This is problem or section 6.3 from our books. I'll give you a second to open that up if any of you are interested in opening it up. But today, like I said, we're going to talk about annuities. And long story short for what an annuity is. So far, we've been talking about problems where we put money into an account and just let it sit there. We don't touch it. We don't do anything. Let it sit there and let it grow. And we're given some interest rate. That's a compound interest problem or a simple interest problem. What if instead of just putting one deposit into the account, we want to make regular deposits? Like that's usually what a person does, right? Maybe if you have a savings account right now, you might, after every time you get paid, put a little bit of money into your savings account. If we make equal payments into an account at equal time intervals, so if I say I want to put in $100 into my savings account every month, that's an example of an annuity. Okay, equal payments being made into an account at equal time intervals. We're going to talk about how annuities grow. So if I put $100 into my savings account at the end of every month for 3 years, how much money will I earn? And then remember, these are accounts that are earning interest. So you're not just going to have the money that you put into the account. That money is also going to earn interest. And since the money is being put into the account at different times, the amount of interest that each payment earns will be slightly different. So we're going to talk about, like I said, come up with a formula for computing what the future value of such an investment would be. I love this section because we start off with this interesting little problem. It says two twins graduate from college together and start their careers. Twin one invests $2,000 at the end of each of the first 8 years he worked into an account that earns 10% interest compounded annually. After the initial 8 years, no additional contributions are made. Okay, so he's at the end of every year when he first starts working, boom, $2,000 into this retirement account. Doesn't touch it again. Just for those 8 years, and then I guess he quit after 8 years. He decided he didn't want to invest anymore. Boom, he's done. The other twin two, doesn't invest anything at all for the first 8 years. And that happens sometimes, people get a job and they're young and they're like, oh, I can hold off on investing. So he doesn't invest anything at all. But then after the first 8 years, so starting in year 9, he invests $2,000 at the end of each year. He continues this for 36 more years until age 65. That's when he retires. I think that's the current retirement age. Yes, 65. This account also pays 10% interest compounded annually. So both are earning 10% interest compounded annually. One twin invests $2,000 for 8 years and then just stops investing. He lets that money just continue to grow. The other twin doesn't invest anything for the first few years, and then he invests $2,000 for 36 years, much longer. And the question is, by the time they reach 65 and retire, which twin has the larger account and by how much? So by the end of class today, we're going to come back to this problem. We're going to be able to calculate exactly how much money each of these twins have in their account. We're going to look at how much of their own money they invested and then how much is interest. And then we'll see which one of these investment plans is the best. Should you invest $2,000 for 8 years in the beginning of your career and then never invest again? Or should you hold off in the beginning and then, once you start making a little bit more money, invest for the rest of the time? All right, you can think about which one you think will earn more money. We'll get to the answer at the end of today's class. These are examples of annuities because, as I mentioned earlier, if we make equal payments into an account over equal time intervals, we call that an annuity. If a person makes equal payments, investments, or deposits on a regular basis, so it can either be every year, every month, every week, every day, it just has to be regular time intervals, that person is contributing to an annuity, okay? The idea is we want to figure out how much you end up with that account, how much you end up with in that account by the end of this investment. The sum of all of the payments plus the interest earned on those payments is called the future value of the annuity, or the future amount of the annuity. Notice this terminology, future value. We've seen this before, okay? You can have future value for a regular compound interest problem. You can have future value for an annuity. You can have future value for simple interest. Future value just means how much money do we have in the future at the end of this investment. Future value of an annuity has its own formula though, and we'll go over that in just a second. There are two different types of annuities. Like, let's say I'm gonna put $100 into my account every month. If I put that money in at the beginning of the period, so if I put it in at the beginning of the month, the first of every month, that's called an annuity due. If the payment is made at the end of the month, it's called an ordinary annuity. The annuities that we're going to look at in this class are going to be ordinary annuities. So an ordinary annuity is when the investment is made at the end of each interval. So if I say, oh, I'm going to invest, the twins, they're investing $2,000 every year. It's at the end of the year, they invest that money into the account. That's an important distinction because that'll change how much interest it's earning. It doesn't earn money for the first year because you don't put it into the account into the end of the year. All right, so equal payments made at equal time intervals into an account is called an annuity. And we're about to determine how to find the future value of that. So we'll start off with a very simple example. And this way, you can kind of understand what's happening with each of your annuity payments, and then we'll see how the future value is actually calculated. So we'll start off simple. We're going to invest $100 at the end of each year for 5 years into an account that pays 10% interest compounded annually. So this means at the end of every year, we're going to add 10% of the amount that's in the account for each payment. Yeah, so it gets a little tricky. The tricky part here is we're not just putting one lump sum and calculating the future value of that. We're putting $100 at the end of each year for 5 years. So that's going to be 5 different $100 payments. And for each of those 5 payments, we have to figure out how much it grows to at the end of the investment. Okay, I heard someone unmute. Does someone have a question? All right, then let's go. So we're going to break this down year by year. How much money is in your account at the end of year 1? Well, you invest nothing in the beginning. At the end of the year, you put in $100. So boom, at the end of year 1, we have $100. I think we can all agree there, right? Pretty straightforward. That's the first payment. Now, how much money is in your account at the end of the second year? So at the end of the second year, you invest another $100. This is the second payment. But what happens with the first $100 that you've invested? The money that you invested at the end of year 1, it's now been sitting in the account for a year. So it's earned 10% interest. So the amount or the money from the second account, or the money at the end of the second year from the first payment, is now going to be 100 times 1.10. That's the $100 you invested, plus it's earned 10% interest for that year that it's been in the account. All right, so again, boom, you throw in $100 at the end of the second year, and then the money that was in there from the first year, it's still there, plus 10% interest for that money. All right, now on to year 3. This is where things get very interesting. So at the end of year 3, you throw in another $100. And then what happened with that money that you put in at the end of year 2? Well, now that money has been sitting in the account for 1 year. So the money that you put in at the end of year 2 has earned interest for 1 year. So we have 100 times 1.10. This is the second payment that you made for the end of year 2. And then now working backwards again, how long has the money that you put in at the end of year 3 been, or end of year 1 been in the account? You put it in at the end of year 1, and then it was in the account for the entire 2nd year and in the account for the entire 3rd year. So it's earned interest for 2 years. So now this amount is going to be 100 times 1.10 to the 2nd power. That 1.10 to the 2nd power is because you're earning interest on that money for 2 years. All right. I'll pause really quickly. Any questions about this so far? Basically, what's happening is for every payment that we make, it's its own compound interest problem. We have to figure out for that payment for at the end of each year, how much does it grow to, and also determine how long is it earning interest? How long is it in the account earning interest? All right, 2 more years and then we're done. For the 4th year, this is the money put in at the end of the 4th year. The money that was put in at the end of the 3rd year has now earned interest for 1 year. The money that was put in at the end of the 2nd year has now been in the account for 2 years. And then, I was saying payment, sorry, 2nd payment. And then the first money that we put in at the end of the 1st year, it's in the account for the 3rd year, the 4th year, and the 2nd year, the 3rd year, and the 4th year. So that's 3 years of interest being earned. Oh gosh, first payment. All right. Now, finally, you're doing this for 5 years. Finally, at the end of the 5th year, this sequence of sums tells us how much money we have. We have the money that we put in at the end of the 5th year. That's just going to be $100. It hasn't been sitting in the account any time to earn interest, so it'll just be $100. That's it. Boom. You put in $100 at the end of the 5th year. That's it. It doesn't grow. The money that you've put in at the end of the 4th year has earned 10% interest. So it'll be, because it's been in there 1 year. So 100 times 1.10. The money from the 3rd year has now been in the account for 2 years earning interest. The money from the 2nd year has now been in the account for 3 years earning interest. And finally, the first payment that you made, that's the money that you put in at the end of the 1st year, sits in the account for 4 years earning interest. All right, so again, what is happening here? These are 5 different compound interest problems. For every payment that you make, you have to solve your own compound interest problem to figure out how long that payment is going to be in the account, and then how much interest it's earning. Okay, and it doesn't really look like a compound interest problem maybe to you right now, but let me help a little bit. So for the first payment, that's $100, the principal, plus 1 plus 1.0 over 1 to the 1 times 4 power. It's 10% interest compounded annually. So this just simplifies to 100 times 1.10 to the 4th power. All right, so this is how an annuity works. Put in a payment, it's like that one payment is like its own compound interest problem. It's going to grow to a certain amount depending on how long it's in the account, okay? Obviously, what if we're investing for like 50 years? We don't want to make this long sum of 50 payments. So this must simplify some nice way. It actually does. On the next page, we're going to look at the future value of an annuity formula. It's a formula that kind of simplifies this entire process. So we don't have to calculate each payment individually. We'll have one formula that we can use, and we just need to know how long we're investing the money, how many payments we're making, the amount of the payments, and the interest rate, and the compounding frequency. If we know all of those things, we'll be able to figure out the future value. All right. So the future value of an ordinary annuity formula. If R dollars is deposited at the end of each period for n periods. Notice it says n periods, not years. Into an annuity that earns an interest rate of I per period. Again, this is the interest rate per period. That's going to be different in a number of periods. This is different from what we did before. The future value of the annuity can be found by, this is read S equals R times SN angle I. I don't usually use this notation, so you don't have to really know it. You'll see it though in print if you ever study this again. So I'll go through the definition of what that is, but we don't actually use it. This is what you'll need. S equals R times 1 plus I to the n power minus 1 all divided by I, where I is the interest rate per period and n is the number of periods. And then again, this notation, S N angle I, it just means how much would a $1 investment grow to over this time? So if your R is $1, what would you get? And that is just given by this term that's in the brackets. All right, so this is the formula we're going to use to calculate the future value of an annuity. If we know our payments, we know how many periods we're making these payments for, we know the interest rate per period, we can plug those things in and figure out the future value of the account. All right, write that formula down. We're going to use it for all of the problems going forward. First example. Now I want you to look at this problem and then try to determine, like, well, how would we know that this is an annuity problem rather than just a regular compound interest problem? Notice the similarities between them and then see if you notice a difference. It says Richard Lloyd, why do we need to know his last name? Richard Lloyd deposits $200 at the end of each quarter in an account that pays 4% interest compounded quarterly. How much money will he have in the account in 2 1/4 years? Now, just looking at this kind of looks exactly like the problems we had last class and we saw in the lab earlier. We were talking about regular compound interest. What's different here? At the end of each quarter. Remember, with an annuity, you're not just putting one payment into the account and letting it grow. You're putting multiple payments over and over into an account. So look for key phrases like that at the end of each quarter, at the end of each month. That lets you know when you have an annuity versus just a regular compound interest problem. All right, so this is a future value of an annuity problem. When we have future value of an annuity problems, remember our formula is S equals R times 1 plus I to the n minus 1 over I. Did I get that right? Make sure I didn't write that wrong. Okay, 1 plus I to the n minus 1 over I. I like to come over to the side and calculate the values of R, I, and N that we're going to plug into the formula. First thing, what's R? R is the amount of your payments that you're putting in. We are depositing $200 into the account at the end of each quarter. All right, that's not so bad. Now, for I, this is the interest rate per period. Now, it bothers me a little bit because the N that we see here is not the N that we used for the compound interest formula. This N represents the number of periods, not the number of times you compound. So please be careful with that. This I is going to be the interest rate per period. So that's the interest rate, 0.04%, because it's 4%, but it's being compounded quarterly. So we're going to divide this by 4. It gives us 0.01. So you'll take the interest rate given and divide by the compounding frequency. If we have 4% interest compounded quarterly, that's equivalent to 1% interest each quarter. All right. And then for N, this is the number of periods. Our periods are quarters. So we have to figure out how many quarters are there in 2.5 years. I'm sorry, not even 2.5, 2 1/4 years. Well, how many quarters are there in 1 year? 4 quarters. How many quarters are there in 2 years? That would be 4 plus 4, 8 quarters. And then we have another quarter. So this should be 9. How can you figure this out? Take the number of years, 2 and 1/4, and multiply by the compounding frequency, 4. Okay, this will give us 9 quarters. And then at 0.01, this is the percent per quarter. All right, once you have these two things, then it's pretty easy. Throw this all into the formula and just be very careful when you are using your calculator to simplify this. Take it one step at a time. Remember the order of operations. We'll need to simplify what's in parentheses, raise it to the exponent, subtract the 1, and then divide by I. And then the last step would be to multiply by R. Before I go on and do this, are there any questions about the values that we got for R, I, and N? Cool. Then let's plug these things in. Sorry, this is all summarized here. I did it already though. What are we looking for? The amount in the account after 2 1/4 years. What do we know? We know R, N, and I. What formula are we using? This one. So when we plug in our information, we get S equals 200 times 1 plus 0.01 to the 9th power minus 1, all divided by 0.01. Now, when you do these types of problems, I will be looking for you to first tell me what formula you used, and then second, show me what numbers you actually plugged into the formula. So I'll be looking for something that looks like this. From here, you can simplify in as many or as few steps as you would like. If you want to try to plug this whole thing into the calculator and hit enter, that's fine. But please, everybody take out your calculators now, and let's try to simplify this step by step. Half of the problem in this section is figuring out the right formula to use. The other half is typing this stuff into your calculator the correct way. So you definitely want to practice this as we're going throughout. I usually simplify this part first. So simplify the what's in the parentheses. 1 plus 0.01 is 1.01. And then you can compute this entire numerator. 1.01 to the 9th power minus 1 gives us this long decimal. Notice I keep the entire decimal. I do not round in the middle of the problem. Okay, then we're going to divide this by I. 0.093685273 divided by 0.01 is 9.36852728. And then last step, multiply the term in the brackets by R, which was 200. And this gives us $1,873, and we're going to round to the nearest cent, so 71 cents. Again, this is broken down step by step. If you don't want to show all of these steps and you just simplify it all in your calculator at once, that's fine by me too. Just be very careful. And as we're going through these practice problems in class, and also you're reviewing your homeworks, make sure you practice using your calculator and showing the steps exactly as you would on a test. Again, what I will be looking for is the formula you used and what you actually plugged into the formula. So you have to at least show this step, and then you can simplify in 1 or 2 or 3 or however many steps you want. All right, I'm going to pause here really quickly. Any questions about this? All right, I want to take this a slight step further. It says we're going to end up with $1,873.71 in the account. Great. How much of that is money that we actually put into the account, and how much of it is interest? So a little quick note down here. Remember, we put $200 into the account every quarter. How many quarters did we have? 9 quarters, because it was for 2 and 4th years, right? So how much money did we actually put in? $200 for 9 periods is $1,800. So we put $1,800 into the account of our own money. Okay. Then how much interest was earned? This is, oops, the amount invested, $1,800. Then the rest of the money, 1,873.71 minus 1,800, which is $73.71, is the interest that we earned. All right, that wasn't asked of us here, but I want us to have a good understanding of what these numbers are representing. So we're putting this money into this account over time, $200 every quarter for 2 and a 4th years is $1,800 that you end up putting in. And over that time for 2.5 years, you end up earning $73.71 in interest. All right, any questions about this one? Then back to our twins. All right, so now we have the tools to calculate how much money each twin has in their account. Just to refresh your memory, twin 1 put $2,000 in the account at the end of every year for 8 years, only for 8 years, and then didn't invest anything else. He just let that money sit in the account and grow. Twin 1 didn't invest anything for the first 8 years, and then he started investing $2,000 at the end of every year for 36 years. And we want to figure out how much each twin has. We're going to start with twin 2. So from twin problem, we used at the start of class, how much does twin 2 have at the age of 65? What are we looking for? We're looking for the amount, the dollar amount in twin 2's account after 36 years. And that 36 was given to us in the problem. We're told that in the beginning. All right. What do we know? Well, we know that he invested $2,000 at the end of every year. We know the number of years, 36. And we know the interest rate was, if we go back to the beginning of the problem, it was 10%. So that's R, I, and N. R is $2,000. The interest rate per period, our period is yearly, so it'll just be 10%. 10% divided by 1 is 10%. And then the number of periods, again, this is yearly, so it'll be the same as the number of years that he's investing, 36 years. All right. So using our future value of an annuity formula, and again, this is an annuity because he's making multiple $2,000 payments every year, equal payment amounts at equal time intervals. So S equals R times 1 plus I to the n minus 1 divided by I. We simplify this. That's 2,000 times 1 plus 0.10 to the 36th power minus 1, or 2,000 times 1.10 to the 36th power minus 1. That simplifies to, if you simplify the numerator inside of the brackets, 29.91268,053. And we're dividing that by I, which gives us 2,000 times 299.1268053. Again, do not simplify these decimals in the middle of the problem. Don't simplify into the very end. If we multiply this, twin 2 ends up with $598,253.61. All right. Not too bad, right? Any questions about this calculation? You understand that R is the amount of the payment. The interest rate was 10% per year. We're compounding annually here, so I is 10%. And we did this investment for 36 years, or we made these payments yearly for 36 years, so N is 36.
So I just have a question about the decimal. Don't like round down or round up at all. Just keep that long decimal the whole time, right?
Yes, until the very end of the problem. If you round in the middle of the problem, it'll throw off your final answer.
Okay.
Yeah, so if you just saw, like, if you were at this stage and you're like, okay, well, I'm just going to call that about 31. Then you'll have 31 minus 1, which is 30. So your numerator is 30, and you're probably thinking, oh, well, that's really, really close. It'll still end up throwing off the final answer, probably by a few cents, but it'll get you the wrong answer. So just do not simplify any decimals until the final step.
Okay, thank you.
Round any decimals, I should say. Any other questions?
I have a question. For the second step, when it's 1.10 to the 36 minus 1, I got 29 point something, like decimals. Is that right, or am I doing something wrong?
That's right. 29.9126. That's what you got?
Yeah.
Okay.
But when I put everything together, I don't know. I don't know what I'm doing wrong.
I don't think you're doing anything wrong. You said you got this answer, and that's the number. Why do you think something's wrong? At this step, the 1 hasn't been subtracted. So this 30.912688053, that's just 1.10 to the 36th power.
Okay.
It sounds like you just went from this step to this step. Oh, sorry. This step to this step, which is perfectly fine. Again, you don't have to simplify in all of the steps that I do or show here. But it sounds like your numerator simplified to 29.91268. And I'll put it in my calculator again with you guys. 1.10 to the 36th power minus 1. Yeah, I got the same answer, 29.912688053. All right, and again, everybody should be practicing this because it's probably like, oh, it's just not too bad. This looks easy. We're given the formula, I can do this. But you want to practice entering in this stuff into your calculators for sure. Any other questions? All right, now let's go on to twin 2. Now, twin 2's problem is a little bit different because remember, I'm sorry, twin 1. Twin 1, she only invested for the first 8 years and then just stopped investing. But the money in the account would still be growing because it's still earning interest. We're just not adding any new payments to it. So we're going to have to actually break this up into 2 different parts. First, for the first 8 years where you're putting in $2,000 at the end of the year, that's an annuity. So we'll calculate how much that annuity grows to. And then while the money is just sitting in the account and no other payments are being added to it, that's just like a regular compound interest problem. So we'll have to break this up 2 different ways. So from the twin problem, how much does twin 1 have? We're looking for the dollar amount in twin 1's account at age 65. So that's how many years? The money's going to sit in the account for 36 years after the first 8 years of investing. Okay, what do we know? Twin 1 invests $2,000, so that's R at the end of every year. The money is still earning 10% interest per year, and twin 1 only invested this much for 8 years and then said, I quit investing for retirement. Okay. So if we calculate the what this annuity grows to at the end of the 8 years, we have to use our future value of an annuity formula. And this gives us 2,000 times 1 plus 0.10 to the 8th power minus 1 divided by 10. Simplifying this gets us all the way down to $22,871.78. Now, as you're simplifying this, I want you to remember that this is not the amount that twin 1 ends up with at 65. This is just after those first 8 years of putting the money in. So the money is still going to be sitting there for another 36 years earning interest. Okay, so After the 8 years of investing, twin one ends up with $22,871.78. Is it correct that twin one's account has approximately this much money? The answer is no. Why not? After 8 years, the account has this amount, and it continues to earn 10% interest compounded annually for 36 more years. So now for the second part here, we're going to take this amount that we just calculated and use the compound interest formula to figure out how much that grows to if it's earning 10% interest for 36 years and we're compounding annually. So what formula do we need to use in order to solve this? Our regular compound interest formula. Before we had an A here, A or S, same thing. S equals P times 1 plus I to the N. This is the same as P times 1 plus R over N to the NT. Well, we'll call this one M, R over M to the MT. Our compound interest formula that we've been using previously. That's what we're going to use now. And in this case, P is going to be the $22,871.78. I would be the same as R over M, which is 0.10 over 1, or 0.10. And then N is going to be 36. Let's plug that in. So after the first 8 years investing into the annuity, then twin one stops making annuity payments, but the money still is in the account earning interest. And after 36 years, the money in the account ends up growing to $707,028.03. So, a little bit surprising, but the person who only invested for 8 years in the beginning and then stopped putting money into their retirement account actually ends up with more money. Okay, so let's look at a little summary of what we have here. And also let's think about how much of their own money the twins invested into the account and how much is actually interest. So for twin one only put in $2,000 at the end of the year for 8 years. So that's $16,000. And they ended up with about $707,000. Twin two didn't put anything in the beginning. So they decided to hold off on investing into a retirement account. And then after 8 years, they started investing. For 36 years, they put in $2,000 every year. That's $72,000 of their own money that they put in. And that grew to $598,000, which is still a nice investment. But what's a bit surprising here, and it's my warning to all of you, some of you may have jobs already where you're able to invest into a retirement account. If you are, the moral of this story is invest early. Although twin one contributed less money of their own out of pocket, they started the investments earlier so that money started earning interest earlier. The earlier your money starts earning interest, the better you come out in the long run. So if it's possible for you, like if your first job, you may be thinking, oh, I have a very long time before I retire. I don't need to put this money into a retirement account. If you're able to do it, do it. Definitely start investing early. So this is sometimes surprising to people because clearly the second twin put in way more money, but ends up with less money at the end. And that's because when it comes to annuities or when it comes to compound interest in general, the longer the money is earning interest or the earlier you start making the investments, the better. All right. Any questions about this little summary at all? All right. Oh, the exact value. So twin one contributed $56,000 less than twin two, but ends up with $108,000, almost $109,000 more than twin two at retirement. All right. Last little topic we need to talk about, and this will be our last problem, is called a sinking fund. Some borrowers, like municipalities, so cities, may have a debt that is to be paid in a single large sum on a specific future date. So I borrow some money and it's like, okay, I'm going to owe you $10,000 in 5 years. But you're like, I don't want you to pay me over time. I just want my whole $10,000 in 5 years. Okay. Don't pay me $1,000 every 6 months. I want the whole lump sum altogether. So when this happens, instead of just, paying the money all at one time at the end, they will have to do that eventually. But you can set up something called a sinking fund, where you make payments at equal time intervals into an account that earn a little bit of interest. So let's say I have $1,000 to pay you now. You don't want it now, you want it later. I'm going to put this $1,000 into an account and let it earn a little interest. So I'll have the $1,000 plus a little interest to pay you. And eventually all of these little payments should add up to, and the interest should add up to the amount that I owe you. And then on the day that I owe you the money, I can take all of this money out plus the interest and pay you. Why is this helpful? Well, the person who owes the money ends up having to pay a little bit less because they're not just paying back, or what's a good way to say this? They're not just giving you the money that they invested, they're also earning a little bit of interest. So that lowers the amount of money out of pocket that they have to pay. Hope that made sense, but we'll do an example of this. So some borrowers have a debt that should be paid at a future date. If these borrowers make periodic deposits that will produce that sum on a specific day, we say that they are establishing a sinking fund. So you're putting money into an account at equal time intervals. The monies that you are depositing are going to grow to that certain amount that we know that we want. And again, it's earning interest. This is called a sinking fund. Basically, it's a future value of an annuity problem where we know the future value that we want. We're trying to figure out what are the payments that we need to make. So how much should we invest at these equal time intervals to grow to the amount that we're going to end up owing? All right. Last example. A company establishes a sinking fund to discharge a debt of $300,000 due in 5 years. So we owe $300,000 in 5 years. In order to pay this off, we're going to make equal semi-annual deposits into an account. The first one is due in 6 months, okay? If the deposits are placed into an account that pays 6% compounded semi-annually, what is the size of the deposit? What is the size of the deposit? So again, this is a future value of an annuity problem where we know what future value we want to end up with, but we need to figure out R, the amount of the payments that we're going to make. All right, so what are we looking for here? The size of the deposit. What information do we know? We know that the future value is going to be $300,000, that's S. We know that we are making, let me see, how did this N come? N is equal to 5 years times semi-annual payments. So if you're making semi-annual payments for 5 years, how many payments is that altogether? 10. And then for the interest rate is 6% compounded semi-annually. So I would be 0.06 over 2. That's 3% each 6 months for every semi-annual period. All right, and then throwing all of this into our future value of an annuity formula. We'll have S is equal to R times 1 plus I to the N minus 1 over I. That's 300,000 equals R times 1 plus 0.03 to the 10th power minus 1 over 0.03. Now, here we're solving for R. So we're going to need to simplify this entire bracket expression until we get one decimal. And our final step will be to divide both sides by that decimal. So 1 plus 0.03 to the 10th power minus 1. That simplifies to 0.343916370. And then if we divide that by I, we end up with 11.46387931. Now to solve for R, we need to divide by this. 300,000 divided by 11.46387931 tells us that our payments should be $26,169.15. All right, so our solution. How much should we deposit every 6 months into this account in order for it to grow to $300,000? The semi-annual deposits should be $26,169.15. All right. Now, last little thing, so I can convince you that this was a good idea for the municipalities to put the money into this account. So if we make payments of $26,169.15, for how many periods are we doing this? Semi-annually for 5 years, for 10 periods. That gives us $61,691.50. Okay, paid. So this is how much money that the municipality actually ends up putting into the account. But how much does it grow to? It grows to the $300,000 that they wanted. They only put in $261,000. So even though they owe $300,000, they only ended up having to invest or pay $261,691.50. So this saves them a little bit of money because they're basically able to let their money earn interest and use that interest to pay back the loan as well. All right, I will stop here with 2 minutes to spare. I think one of these sections we don't have a lab for. I think 6.3 does have a lab though, so let's see. Oh no, they all have a lab. All right, so for today, I would like for you guys to do the lab for section 6.3. These are all future value of an annuity problems. So you're going to be using S equals R times 1 plus I to the n minus 1 over I. Pay attention to how you find the values for I and n. Remember, that's n is the number of periods you have altogether. I is the interest rate per period. And then how many problems we have here? 4. We have 4 problems here where you either have to figure out the future value or figure out the amount of the payment. That would be a sinking fund. They're all pretty straightforward. So for the first one, you're figuring out the future value. You're finding S. How much money will be in the account after 10 years? For the second one, it says, how much should you deposit each year? This is finding R, the amount of the deposits. Again, how much should I deposit? This is finding R. And then the last one, I open a sinking fund account and deposit $750 each year, assuming an 8.75% interest rate. How long will it take the account to grow to $20,000? So you want to figure out how many payments you have to make in. That one's an interesting one. You're going to end up having to use logs for number 4. All right, so I will stop here.